All right. So, so my talk is about the active tectonics in Western Taiwan, but actually in the end, I'll sort of talk about the short-term, long-term erosion and then uplift in the entire Taiwan. Okay. So before I dive into the talk, I just want to talk a little bit about myself. So I'm from Taiwan, obviously, and Taiwan is an island made of a plate collision. So it's a collision between Eurasian plate and Philippine Sea Plate. So currently the Philippine Sea Plate is moving roughly 82 millimeter per year. So that is roughly twice faster than the collision or the plate motion in California. This is a quite peculiar geologic setting that the Philippine Sea Plate is subducting underneath the Eurasian plate in the north. So here you can see here where the Ryukyu Trench is located. But in southern Taiwan, actually, the Eurasian plate is sort of beneath the Philippine Sea Plate, and the reason is because the Eurasian plate was attached with this South China Sea Plate that you are not seeing right here. So that adds all the complexities in Taiwan, and it makes the geology so interesting. But what really made me excited about geology, or even interested in geology, was this Chichu earthquake in 1999. I was still a high school student at the time, and then I still remember at the time we listened to radio, and then that earthquake woke everybody up. I guess my hometown was roughly 100 kilometers or 70 miles away from the earthquake, and the earthquake happened roughly at 2 in the morning. And that obviously woke me up, and then woke everybody up because you can hear all the noise and all the shaking. When you're a teenager, you normally don't talk to your parents that much, but that was the moment you run to your parents and you hug each other because you don't know what's going to happen. And also we didn't have the proper training to know where you should be hiding. Okay, so the next day, we saw the TV news and realized actually it caused a huge damage. And you can see there's a photo that shows a broken bridge, and it also shows you a cliff or a waterfall. So that waterfall did not exist before the earthquake. So that was the earthquake that brought roughly almost 20 meters of uplift at that very spot. And you can see they are human for scale. And now the waterfall is pretty much gone because after almost 20 years of erosion and typhoons and all the water dumping onto the island, that just increased or accelerated erosion. And then also those are pretty soft bedrock. So now this waterfall is gone. So when I was an undergrad, I was in this research group, and then my advisor introduced InSAR to me. And then the first thing I saw was a interferogram of the Chichu earthquake. So here, the white line here shows the Tulumpu fault. That is where the fault ruptured during the earthquake. And you can see there's almost no information in the hanging wall. That is because there's so much amount of deformation. But in the footwall, you actually can see pretty coherent pattern. So I was so fascinated by this. I didn't understand what InSAR is, but I was really fascinated. So I decided to just stay on and then study InSAR. And then even, 18 years later, I'm still studying InSAR, just with a little bit more advanced technique and a slightly better satellites and all the open source free available data. Back to that time, we have to buy those images. Okay, so here just some quick review of what we are going to be talking about today. So I want to begin with the earthquake cycles in case some of you don't know this already. So this is a really simple model that we are imagine that the whole world is made of 2 plates or 2 blocks. And then there's a fence on the top of the block. And then the 2 blocks is separated by this fault. So during this interseismic process, that is the fault moving past each other, and you can have some energy stored on the fault. So what happened here is you don't really see any earthquakes, but the fault or the place is for sure accommodating some energy. And you can see there's a gradual deformation or bending of the fence. Okay, so it's a characteristic that you will see during the interseismic process or period. And then at some point, the deformation will be so great, there will be so much energy stored on the fault then the fault will break. And then when that happens, you can actually see the breaking of this fence. So then that is what we call the earthquake or the coseismic deformation. And then that typically accompanied by a lot of ground motion and shaking. So that's why you can see all the shaking symbol on this block. And then soon after this period, we'll call it post-seismic. So that is when the energy or the all of the exerted stress or is going to redistribute. So then we call it post-seismic, and then eventually we'll go back to this inter-seismic, and then this loading will start again. Okay, so to actually account for that, we can build those simple blocks. So eventually we know the two blocks will just pass each other. So that is a block on top showing 3D, and this is a lateral strike slip deformation. Then we can think about this long-term motion being broken into an interseismic motion and a coseismic motion. So here's why there's a plus sign. And you can see the difference between interseismic and coseismic is where it is slipping. So in interseismic, you have a lot of deformation below a certain depth, and then now we call it locking depth. So why there's a locking depth has something to do with the crustal rheology or the friction property of the area. So interseismically, we assume everything above that locking depth is locked. And then that will wait until the moment when it breaks, and then will cause a coseismic motion. So that is what you are seeing here. So we know long term is in this fashion, and then current time, there's no earthquake. So what we are receiving is probably the interseismic, which is shown here. So if you rearrange this cartoon, then we can see an interseismic motion will be equivalent to our long-term block motion minus a coseismic. So then if we know the locking depth of a certain area, and then if you are able to measure this interseismic motion, then you will probably be able to estimate what is a coseismic and then the potential seismic hazard of this area. So this is what we are going to talk about today, for majority of the talk. So in other words, if you have a lot of instruments to measure this interseismic motion, then you can probably do a better job in predicting the coseismic forecast. So ideally, so this is the idealized interseismic motion showing the white arrows. And then the contour lines that you see in the bottom, that is where you will assume where that interseismic motion working on along below this locking depth. And then during the coseismic motion, then you will see the white arrows now record the motion during the earthquake. And then here's a fault plane, and you can, based on the observation, and you can infer, or you can estimate the coseismic slip that is showing the red color. So that's say when you have more and more arrows on the surface, then you can probably do a better job in investigating that slip distribution below the depth. So in other words, we want as many GPS as we can in order to get this information. But there comes to a problem that we can't put GPS everywhere on Earth, and they are pretty expensive, so we can't do it. Then one replacement will be by using this InSAR. So this is a really simple cartoon showing you how InSAR works. So essentially, it emits radar signals through, and then it will hit a ground target and return back to the satellite. So if you do interferometry between those flybys of the satellite, then when there's a certain event like this is a South Napa earthquake, then you will be able to detect the surface deformation. And the fringes represent the amount of surface deformation. So you can think about the fringes as when you are reading elevation contour lines. So if you know the contour interval, then you are able to estimate elevation, right? But now those are not elevation, this is deformation. So that is the easiest way we can quickly convert the amount of deformation that is associated with some surface deformation. Okay, so I just spent almost 10 minutes, and now let's go to the talk. So Taiwan, as I introduced earlier, it is in between the Eurasian plate and the Philippine Sea Plate. So here you are seeing a geologic map. So the color here from west to east, that represent a gradual increase of metamorphism. So on the west side, that is shown in brown, pinkish, those are the sedimentary rock. And then shown in green here are, or to those crosses, those are the metamorphic rocks. And then more east, that will be a higher grade metamorphism. Here you are seeing a thrust fault here. So that's the major plate boundary between Eurasian plate and Philippine Sea Plate. So in the Philippine Sea Plate, the rock made out of this eastern part of the island is mostly volcanic rock. As I mentioned earlier, this is a GPS displacement, and then you can see the general deformation is roughly 80 millimeter per year. And then here you can see how this deformation is distributed. So you see there's large amount of deformation in the south, and then there's also a change of orientation. So here we know this is in the southwest part of Taiwan, we're experiencing some kind of tectonic escape. And then you can also see the seismicity in Taiwan. So here on the right-hand side, the color represents the depth. So you can see all the seismicities are getting deeper and deeper toward east. Oops. Okay, so this is a map of continuous GPS in Taiwan. I think currently we have roughly 500 continuous GPS stations on the island. In terms of the size of the island, it is, if you know how big Switzerland is, it's actually smaller than Switzerland and a little bit bigger than Belgium. So it's a very small island, but we have a pretty high density of continuous GPS. So it's one of the highest density network in the world. But I wanna show you that even we have this many stations, still not able to capture all the deformation. So I wanna draw your attention to this this spot where it is in part of the Western foothills. So in 2004, the Highway Bureau did a new tunnel that goes through this Western foothill. Soon after they dug this tunnel, they found there are a lot of cracks. So they thought, well, that might be just some kind of groundwater flow in redistribution, so that caused the cracks. But 10 years later, if you look at this spot again, you can see there's a very solid offset. If you look at the ceiling tiles or the lighting, you can see there's a very clear ramp. So that was roughly 1 meter of uplift on one side. So that documents how fast those the tectonic rate is in Taiwan. So here our motivation question will be, can we use geodetic data to estimate the interseismic fault slip budget? And what is a slip budget in any way? And based on those geodetic observations, can we do a good job on highlighting which fault is more active than the other? And then given the measurement uncertainties. So this is a GPS data we are going to be using. So if you look at InSAR, then this is a descending MVSat data that was recorded in between 2005 and 2009. So here we are seeing a lot of those little colored dots. So each dot represents one InSAR pixel that we consider to be stable, and it's recording the data continuously. Blue color here means the surface motion is going away from the satellite, and then red or warm color means it's moving toward the satellite. And this is a descending. The white arrow here represents the loop direction. So that means blue means moving away. So that could be either moving toward west or moving downwards. And this is another example that is the ALOS-1 data collected between 2007 and 2010. So this is a descending track. So the arrow here shows is looking toward right. And then again, blue means moving away, warm color means moving toward the satellite. So if you compare ascending and descending on this map, then you can see there are something consistent, something different. For example, in the coastal area, you are seeing generally blue color here or blue color layer. So that indicates those deformations dominantly subsidence. So indeed, those are surface subsidence driven by groundwater pumping. If you are looking at the southwest corner, like here or here, then you can see it's blue color on one side and red color on the other one. So that indicates it's probably dominated by horizontal motion. So this is that southwestward motion that indicates the tectonic escape. So by combining ascending and descending, and then by also using GPS to account for north-south, then we are able to compare all the descending, ascending, and then see how they can we can use them to calculate a 3D displacement. So here is a comparison between GPS and InSAR with the 3 different tracks. So the one on the left is descending, and then in the center and then on the right hand side are ascending. The circles are GPS measurement I converted to a line of sight. So you can see, so this is without any adjustment between InSAR and GPS. Then you already can see the color between the background pixel and then the circles are very similar. So that already tells us that the GPS and InSAR are in very good agreement. To quantitatively compare that, we can just draw this GPS with InSAR comparison. So the dashed line here indicates where the one-to-one line is. If you are seeing that the circles are along the one-to-one line, that means they are in perfect agreement. If you are away from that, that means they are deviated. So the blue color, the blue circles are the original data comparison. So you can see they are actually something that InSAR is generally under predicting the amount of displacement. So if you're looking at those blue colors in a higher value, higher positive value. So we did a plane fitting between the GPS and InSAR, and we are trying to correct this first order deviation. And after doing this correction, then you can see those are in the orange circles, and now they are in a much better trend. Okay, so based on those results, then we did a 3D inversion to get the 3D displacement. Then this is what the surface displacement in the 3D. Why I say displacement is really velocity. Okay, so InSAR, both InSAR and GPS are giving you time series, and we separate the annual periodic signal and also a long-term slope. So here I'm just showing you this long-term slope. That is the velocity. So now I'm taking this circle here as our reference point. So that is a specific continuous GPS station. So you can see north of this reference point, you have dominantly eastward motion, and southeast of this reference point, you have dominantly westward motion. And then the north-south motion is relatively small. And also InSAR is notoriously bad at looking at detecting north-south motion, especially for those older generation InSAR. So this is essentially an interpolation of the GPS data. InSAR is actually good at detecting vertical motion. So on the right-hand side, you can see it's actually showing you quite a lot of detail about vertical motion. So here again, we are seeing this huge amount of land subsidence in the coastal area due to groundwater pumping. And also this corner, you are seeing a lot of groundwater pumping. But here, you are actually seeing quite a lot of uplift. So I want to remind you again that tunnel I was just talking you about is roughly here, where my cursor is pointing at. So if we did have those InSAR measurements before the Highway Bureau dug that tunnel, maybe they would have known beforehand that they are digging through an active fault, and then they can be expecting this amount of surface uplift in the tunnel if they had this InSAR data ahead of the time. Okay, so that is the first part about data collection. Now I just show you how what kind of data we are going to be using in our block model that will eventually tell us about the possible seismic hazard. On the other hand, we also want to know the fault information. So the first thing we thought about is to look at the geologic map. So this color image here shows you the detailed geologic map of Western Taiwan done by the CPC oil group. And the thick, you can see there are some thick black lines here. Those are the published active faults identified by a Central Geologic Survey in Taiwan. So I essentially trying to digitize the geologic map and then also to connect the published active fault. So then I make a block that looks like this. So you will probably see that some of this is not realistic at all. Like in the northern part, there's just no faults. And the reason is because there's no data constraint. So all of those blocks are just off-bound. So we don't really need to worry about what is happening. So what we are really trying to focus on today is only this area. And we are, so currently my graduate student, Catherine Robbins, and I are trying to extend this block model to entire Western Taiwan, and then we will be including more recent Sentinel-1 data into this. So hopefully we can have an update relatively soon. Okay, so this is a block distribution, and then if I zoom in, based on the geologic information, then I can assign different locking depth of the fault. We can also assign different fault dip angle and those kind of information based on the geologic map. And then now you might be thinking, this is kind of crazy that we are just mapping a lot of faults, and then there's no way all of them are being active. It's probably just some of them are active and some of them are not. So that is exactly the point why we are doing this. We are trying to map the faults as detailed as possible. And we are going to let the data to tell us how many faults are needed in order to explain our data, given the data uncertainty. So the method is really just a simple block models with some new constraints. So here I'm showing you some strategy that was first derived by Eileen Evans, and she published that in GJI in 2015. And it's actually because she presented that in AGU, and I saw the talk, and I talked to her afterward, and then that's how this work being started, is by after seeing her talk in AGU. Okay, so on the left-hand side, you are seeing 3 blocks that indicate 3 different tectonic plates. So between block 1 and 2, you can see there's a strike slip motion, and then between block 2 and 3, you are seeing some subduction and then some strike slip. And how the block moves is according to where the Euler pole is. So this Euler pole 1 that refers to the center of rotation of this block 1. So it's rotating about this pole, and it has a clockwise rotation. And then block 2 is rotating about here, and it has also a clockwise rotation. But today, if the pole 1 and pole 2 are at the same location, as shown on the right-hand side, then by comparing the relative motion between block 1 and 2, you actually see no relative motion. So then this plate boundary here that was shown as a strike slip earlier now became something that just being grouped, right? So there's just no relative motion. So you can consider block 1 and 2 is actually the same block. So how we decide whether the Euler pole is at the same spot or not can be determined by the data we are feeding into the inversion. So this is a very traditional inversion scheme where you have this L2 norm. So that L2 norm means you are trying to minimize the L2 norm difference between your data, your model prediction, and your data. So here G is a Green's function that tells us about how the certain geometry that can produce this amount of surface deformation. And then the omega here is the block rotations that you are going to, that in specific one scenario. So G times omega gives you the prediction of the data, and then D is the actual data. So here W is your data weighting. So that data weighting can be different depending on the different data. So you can give different amount of weighting for GPS and InSAR based on the data uncertainty. So that is what we do for L2 norm minimization. So for least square inversion, you typically consider sort of a smoothing term that you will do like Laplacian smoothing. But what is different here is we are implementing this L1 norm regularization, which we call it total variation regularization. So what it does is you have this lambda that is going to trying to group different blocks. So if you're trying to group block 1 and 2, and then that can be served as a kind of smoothing because now you have no relative motion between the 2 blocks. You can also try to group block 1 and block 3, and then you can do run your inversion and then see whether this new grouping and then the total residual is improved or not. Then you can determine whether this is a good inversion or not. Okay, so essentially we are trying to use this total variation regularization, what we call it TVR, and then we simultaneously minimize the L2 norm data residual and then the L1 norm data variation between different group combinations. So that's essentially what you're trying to do. Okay, so to demonstrate that, this lambda coefficient can be vary from really low to really high value. So when lambda is really low, that means you have no grouping. So when there's no grouping, that is when you allow all the blocks is free to rotate and free to move. So that will be the scenario I'm showing you on the left-hand side. So every block now is able to move and pass each other and rotate. So when everything is free to move, you have a lot of degree of freedom. So in other words, you can fit your data the best. So this red color here represents the residual. So you can see the lowest residual, which is less than 4 millimeters per year. You can also, and then you can gradually increase that grouping coefficient. So then you can see the number of blocks are going to reduce. And when that happens, you are not going to able to produce low misfit as earlier. So then you are going to gradually increase the misfit. So eventually when you have the minimum or maximum amount of grouping, you have the minimum amount of blocks, which is 3 blocks in this scenario. So you do not fit your data very well, have a highest residual, but the minimum amount of grouping. So what we are trying to do is we are trying to find the number of grouping we want that produce roughly the same level of misfit as our data uncertainty. So based on our GPS and InSAR analysis, we actually can estimate the uncertainty. And then so we know this roughly a little bit less than 4 millimeter per year uncertainty. So when we determine that is where we consider our misfit is the same level of our data uncertainty, then that is our preferred model, and then we call it our reference model. So that is so this is going back to show you the data itself. So this is the InSAR and GPS data, and I'm showing you only the east-west displacement or velocity. On the top is just a quick reminder that the interseismic motion, we are assuming that as a long-term block motion minus the coseismic motion. And this coseismic motion, we can simply call it backslip. So this block here shows you after that grouping, and then this total block motion you are going to get. So this is equivalent to this 2-block model here. So here is then our prediction of the interseismic model. So the center is our prediction, the left-hand side is our data. And then the difference of the center and then the left-hand side is our residual, which I'm gonna show you here. Okay. So if I go back, sorry. So you can, so that essentially tells you how many blocks you actually need in order to explain our data, okay? So you can see a lot of the color are the same, that means they are grouped. So we actually don't need as many blocks as we mapped in the first place. Okay, so based on that, we can then estimate the strike slip and then the convergence slip rate between different blocks. So then here on the left-hand side is the strike slip, and then in the middle will be a convergent. So those are the slip that is above the locking depth. So based on this, then we can estimate the amount of energy that's being stored above locking depth per year. So what we're doing is to estimate the amount of slip multiplied by the fault area. So and then multiplied by shear modulus, because we know moment rate is equivalent to mu AD, right? So mu is your shear modulus, A is your fault area, and D here is actually the velocity. So based on that, we can then estimate the amount of potential moment that can be released above this locking depth. So I calculate this for per decade. So this is the rate multiplied by 10 years. So here the legend says the decade. And first of all, I want to tell you that don't worry about anything that is offshore, because they are not very well constrained by the data. And then also close to a mountain range, we also don't have a lot of data. So those really high values are probably not very well justified. But in this area where we have relatively rich of data, then you can see for every 10 years, for example, in this area, you might be storing something almost like a 5.1 moment magnitude. But this is just a pure estimate from geodesy. in reality, actually, some of them are already released by seismic. So if you also collect seismic data in the same area, then you can actually see some of them are being released by seismicity. So the real true estimate should be this minus the seismic distribution, which we haven't accounted for yet, but we will do in the future. Okay, so from the InSAR data, we can also calculate the strain rate. So that is essentially the gradient of the velocity. So on the left-hand side, showing you the stress slip rate. And in the middle, that shows you the horizontal strain rate, shear strain rate. So you can see there's really high amount of shear strain going on here. And that also being mapped by this high stress slip rate. And this is much higher than anywhere you can see in California. But on the other hand, it really depends on how the length scale you are looking at. So for example, in the central creeping San Andreas, there's a creep in a very short distance. So in that very localized length scale, you are getting very high strain rate. And this on the right hand side, this is a GPS derived strain rate. So you can see the scale is slightly smaller from GPS, and that is also because you don't have as many stations as InSAR. Because here in InSAR, you literally have millions of points. So with InSAR, you can really see a very clear pattern and map of a horizontal strain rate. We can also look at the vertical. So this is a vertical velocity gradient. Then you are actually seeing the majority of this gradient coming from the land subsidence. So here just highlighting where land subsidence are happening. But in the western foothills, you are actually seeing some relatively higher red color that indicates some kind of uplift motion. Okay, so now I'm just gonna highlight a little portion of that, and then I wanna look at a cross-section view of this. And the reason why we like to compare this cross-section is because we do have some geologic-based geologic profile here. So this is work done by Mong-Han in 2017. So she worked on this based on seismic reflection and then some surface geology measurements. So she found actually in the southwestern foothills, all the faults are essentially back thrusts. So here she's just drawing a few back thrusts, and here is sort of a duplex structure here. So we are trying to see, based on our slip rate that we estimate from geodesy, whether that can be explained or whether this geologic structure can explain that. So here is showing you the vertical velocity from InSAR and GPS from west to east. So you can already see there's some actually quite rough structure. Like here, there's a sharp turn of size of InSAR velocity. That already indicates there must be something creeping right here. So if I take the detachment that was mapped by Lebeon, and then we fit in the slip rate that we obtained from our block modeling, then we can predict this amount of surface displacement in vertical. So you can see that's predicted by the red. So you can see it's underestimating what is going on here in this duplex structure. So a few years ago, there was a 6.4 earthquake in southwest Taiwan. So based on the based on the geodetic and seismic data, I was able to infer a new detachment structure. So I infer a slightly steeper detachment here. So I can also use this geometry and fit in the same amount of slip rate that we infer from block modeling. So based on that, I drew this in blue line. You can see it produced a little bit better fit to the GPS and InSAR measurements. But now we are missing this sharp turn. So that probably indicates that this LCB structure is actually creeping interseismically. So that is something we also need to be accounting for in our future updates. Okay, so to summarize my first part, I hope I've convinced you that space geodesy is a good tool to reveal interseismic crustal deformation, not only in Taiwan, but in a lot of places in the world. And this TVR method is a efficient method to estimate fault activity in the interseismic period that can be justified by the data uncertainty. And also in this vertical deformation profile that I just showed you that indicates the fault ramps is within the foothills are all locked, but there's a specific backflow is actually creeping right now. All right, so in the second part, I want to link this with sort of a long-term climate and erosion. So on the left-hand side, you are seeing a roughly 30 years long observation of the sediment flux. So those are just measuring the sediment flux in different major rivers around Taiwan. So here, bigger black arrow indicates a larger amount of erosion rate. So you can see there's huge amount of erosion rate here, and then the southwest and western Taiwan. The number here indicates millimeter per year. So that is actually very big. I think even just this map account for roughly 1% of global sediment flux per year. And then you can see there's a locally high sediment flux in the southwest Taiwan. So the author trying to compare this sediment flux with other typical tools that you do as a geomorphologist. You will assume when a mountain is steeper and higher, it will produce higher erosion rate. And they found there's almost no correlation because all the high mountains are in the center. And then here you actually don't see huge amount of sediment flux rate. So then they compare with seismic moment that was calculated between 1900 and right before the Chichi earthquake. So that is almost 100-year-long seismic record. Then they actually compare those two, and then shown on the right, then you can see there's a very good correlation between a long-term seismic accumulation rate and the erosion rate. So here that I'm curious about this comparison, because if you look at the sediment flux, then you can see the highest sediment flux is actually here. But from a seismic moment accumulation, you actually see there's not very high at this spot. So then how do we compare this sediment flux with the InSAR, which tells us the interseismic rate then? So that would be a different kind of comparison that I'm interested in. And in addition to this decadal sediment flux rate that people can calculate from stream flux, we can also calculate the denudation rate that is based on the Barrier 10 dating. So those are collecting sand samples from the river catchment, and then based on counting the Barrier 10 emission, then you can see how much erosion has happened. So if you assume more erosion also means more uplift, then you can use that to infer the uplift rate or erosion rate in the longer term. So this Barrier 10 normally can indicate sort of 1,000 to 10,000 year time scale of the surface erosion with the denudation rate. So how that works is you assuming this long-term surface elevation is this partial z over partial t. So that is equal to the bedrock uplift rate, which is this u, minus the channel incision rate, which is this KAS term. So A here means the river catchment size, and S here means the surface slope. And then they all scale with some kind of power terms. And so here, if I'm just assuming InSAR telling us a bedrock uplift rate, because this is essentially telling us what is uplifting before it's being eroded away. Because if it's eroded away, we are probably not going to see it in InSAR. So this is a inferred uplift rate just based on the ascending ALOS data. So here I didn't use the MVSAT because MVSAT was not covering the entire Taiwan. So I just used ALOS ascending and then kind of scale with GPS vertical. So and then you can obviously see in the north it's not very accurate, but we are not comparing the northern catchment in any way. So for now we are not going to worry about the uncertainty or the clearly incorrect estimate in the northern part. But the central part is actually quite good. You can see the color background and the circles are in roughly the same scale. So if I just map out the the catchment onto this InSAR map, and then I calculate the mean uplift rate as the entire catchment as a number and plot on the right-hand side. And if I set Western Taiwan and Eastern Taiwan by the main drainage divide, which is roughly where I'm pointing at right now. So catchment 5, 6, 7, 8, and 9 are Eastern Taiwan, and 1, 2, 3, 4, 5 are from Western Taiwan. So then you can see actually a very interesting comparison. For Eastern Taiwan, which is shown in red, you're essentially seeing a very close to 1-to-1 comparison between denudation rate and the short-term uplift rate. I call it short-term because this measurement is only for 4 years. But in the Western Taiwan, the uplift rate is actually around twice faster than the long-term denudation rate. So that was something pretty surprising to me when I saw that. A few years ago, when I saw an AGU talk by Sean Willett, he actually collected another little, he did another Bavarian tank dating for this little catchment here, and where he was finding is roughly 7 millimeter per year of denudation rate. So if I plot that with the short-term uplift rate from InSAR, then that will be located here. So that's pretty close to this 1-to-1 line as well. Oh, and then the contour line here on the map is showing you the precipitation. And then you are not going to see a very clear correlation between precipitation and then the denudation rate or the uplift rate that I'm going to show soon. I think I'm gonna skip the geomorphology part of that. So this is just a stream power term, and then we are doing very similar analysis, but I'm just gonna skip it for now. All I'm trying to say is based on the digital elevation model in Taiwan, we are able to calculate this case and value. So high case and value essentially means either higher uplift rate or weaker rocks. So this is a case and value of Taiwan. So if I do exact same exercise, I map the main catchments of Taiwan and calculate the mean case and value of the individual catchments. Then I'm seeing the plot on the right-hand side. So you are also seeing the slightly more 1-to-1, or there's actually no scale here. So you are essentially seeing a more rapid case and value in the Western Taiwan than in Eastern Taiwan. So we are inferring that perhaps that means in Eastern Taiwan, the landscape has achieved a more close to steady state. So the amount of uplift is just being eroded away, and uplift will be eroded away. So the surface elevation doesn't change that much. But in the Western Taiwan, we are actually still rapidly uplifting because that's part of the accretional wedge. It's where the majority of the collision is happening. So maybe you are producing more uplift than material can be eroded away. So it's still lifting up the mountain more rapidly than the Eastern Taiwan. So that's a main take-home message. So if you compare erosion rate with precipitation, then you can see there's almost no correlation. This is quite surprising because we always assume more precipitation means more, more saturation, and more landslides that also means more landslides. Means more erosion. Another case here, if I compare with the denudation rate, we also don't see a very clear pattern. More surprisingly, if you take a global compilation, you also don't see a very clear relationship between precipitation and the denudation rate. Okay, so for the second part, I hope I convince you that in the Eastern Taiwan, we have maybe achieved a long-term equilibrium. On the Western Taiwan, though, we are actually seeing roughly twice faster uplift than erosion. So this is my main talk, and then I think I still have 2 more minutes. I just want to talk about a topic I think is very important, but we often don't think about very often in earth science. Is the diversity in the earth science topic. So this is a paper compiled last year. So essentially, this is trying to compare whether gender and then the race brings up the diversity. Brings up the innovation or not. So in plot A and B, that essentially shows you that when you have the 100% same gender or same race, you don't have as much novelty as when you have a more diverse distribution. So that's on the left-hand side, you have higher novelty. On the other hand, if you compare whether those novelties impactful, meaning whether the people who brought up the novelty will actually get likely to get into a future research career, or even the work being impactful in the long term, actually then there's a opposite trend. So when you are in the more diverse distribution, actually there's less impactful novelty. So this is a new finding by this group based on machine learning of a really big data set in all STEM fields. Also, you may have seen this already. So specifically in earth science, there's been an increase of number of female PhD by now. However, if you compare the racial distribution, you can see the dashed line here means the total population in the US in a specific race. For example, the red dashed line color here represent the black population, and then the dashed blue represent the Hispanic population. Then you can see the solid line, which is the number of PhDs, growth with the increase of population for Hispanic race, but for Black, actually there isn't a very clear increase of that. So we are really in this situation. We need to think about why diversity and then this gender, in terms of gender or race, why this diversity is important in earth science. If you think about taking the data from European countries, in the upper right corner, you are seeing the proposals application between men and women for all of those EU countries. And you can see there are a lot more male applications than female applications. However, if you consider success rate, there's almost no distinguishable contribution between male and female. So it really doesn't mean that either male or female are, producing more significant contribution. Just the total number is different. So we all know this is important, but we all often feel like we don't know how to address that and how to start. So I just want to share a couple more slides where I saw in different talks. There's something we call JEDI. So JEDI is justice, equality, diversity, and inclusion. So we want to make sure in our earth science we are trying to dismantle the barriers between different gender and different race. We want to make sure we provide a sufficient amount of resources to all different kind of gender and race. And then we also want to bring up the diversity and then make sure we all experience and then we all dismantle those barriers and then also be inclusive. So for example, we want to make sure that in the AGU poster presentation, we don't want to leave anybody alone. Even though this person maybe doesn't speak perfect English or doesn't speak the same language, but we don't want to just skip them because we feel this may be inconvenient. So in our department at Maryland, we have this group, we call it IDEA working group. So the IDEA means inclusivity, diversity, and equality awareness. We have 4 different subgroups. So we have the climate group that we trying to just to understand the internal department dynamics. We have the outreach group. We are trying to reach out. We are trying to develop different teaching materials that we can be applying to the local high school, middle school, or even elementary school. We have the education group where we try to read through the literature, knowing what is the latest research about diversity and equality. We also have the communication groups that we try to communicate with different local funding agencies or different agencies or different local schools. So we have our biweekly department meeting. We actually talk about all of those topics. Each group will present, including myself. And then a lot of those groups are led by students. And then some of the students are in multiple groups. And then again, we all feel like this is very important, but we don't know what to do. So this is actually a paper, written 14 years ago. They do provide some suggestions that, by dismantling this barrier, we can either demonstrate the relevance of the field and opportunity for high-paid careers in it. And we can also develop the partnerships among multiple stakeholders to reduce the leaks from the educational pipeline. We can try to promoting strong mentoring relationships among students and the geoscience professionals. And then we can also try to provide financial assistance when there's necessary. Okay, thank you for attention, and I guess I'll stop here for any questions.
Thanks so much, Mong-Han. We definitely have time for questions. You can either raise your hand, and I think the easiest way to do that is click participants, and then there should be a button to raise your hand, or you can drop a question in the chat, or you can just go ahead and show your video, and then I'll call on you that way as well. Mong-Han, I was wondering, you don't have many observations in the northern part of Taiwan. Is that because you don't have InSAR up there, or you don't have GPS up there?
Well, we do have a lot of GPS there, and then so the InSAR I'm showing you were from those InSAR collected more than 10 years ago. So at the time, actually, there isn't a lot of overlap in the northern part of Taiwan because, the amount of deformation is a lot smaller there. But in the newer data set, we actually have a full coverage of Taiwan. So hopefully we'll be able to update it soon.
Oh, okay, cool.
Yeah, actually a follow-up question to Els. I saw that you didn't have many observations in the mountain ranges in the east. Does that mean the InSAR doesn't have very high data quality in the area due to the steep slopes or snow covering?
It's definitely the steep slope, but instead of snow covering, it's the vegetation. So only mountains that is above 3,000 meter elevation will be covered by snow during the winter time. And also those are seabed data, so they are, more easily decorrelated by the vegetation.
Okay.
But
gotcha.
nowadays, since we have the Sentinel data set, those are collected roughly every 6 days or every 12 days. So we are getting much better quality nowadays.
Mm-hmm. Yeah, that makes sense. Yeah, actually, I have another one. Sorry.
Yes,
so in your block rotation model, maybe I missed that. How did you come up with the initial fault model on which you tested your hypothesis? Is that from geologic maps?
Right. So those are essentially from geologic maps. So in the geologic maps, it will tell you the dip angle and dip direction. And then for the locking depth, those are based on those the main detachment that people have been assuming from seismic reflection data. So we are just taking the detachment as a locking depth.
Okay. So essentially you start with all the faults that were mapped by previously, and then try to see which ones of them are active using the geodetic measurements.
Yeah.
All right, cool, thanks.
Zell, do you want to ask your question?
Sure. Yeah. Thank you for your talk. I was just wondering what the approximate timescale is for the erosion rate to compensate the uplift in, I think it was Western Taiwan, where they're not matching currently.
Very good question. I guess the short answer is I'm not exactly sure. So the erosion rate, they are quite similar when we compare sort of decadal measurements from river flux, and also from a longer term, which is from beryllium 10 dating. So that tells us the roughly like 10,000 year time scale. The InSAR I'm showing here is only from 4 years of data. And then we are essentially assuming for that 10,000 year time scale, the interseismic rate is the same. But there's a problem actually I didn't really talk about. There's a potential problem is the InSAR was collecting was only 7 or 8 years after that Chichi earthquake that we'll talk about. And then the Chichi earthquake was 7.6. So 7 years after the 7.6 earthquake is probably still a lot of post-seismic deformation coming in to contribute that uplift rate I was measuring. So again, by doing this again for Sentinel data that started from late 2014 to today, we have another 10 years after. Right now we have 20-year post-earthquake measurement. So maybe that will be closer to the inter-seismic. So we can compare whether the latest uplift rate we estimate can be more comparable, or whether or not there's a balance or not non-equilibrium topography.
Thank you.
Mm-hmm.
Shahan, do you want to ask your question?
Oh yeah, hi Mong-Han, very nice talk. So when you measure the deformation with InSAR, is it assumed just to be uplift? I mean, isn't denudation happening at the same time when the uplift is happening?
Yeah, this is a very good question. I think I'm just making a really big assumption that if there is an erosion, then that is going to remove that stable pixel. So
Okay.
I'm kind of just assuming everything I'm seeing is the uplift. But of course, that is something that needs to be justified by more detailed work. So I'm making a really big assumption here.
Okay, so you're assuming that the erosion is going to decorrelate the pixel, while the stable pixels are just like uplifting, like the. Okay,
exactly.
I see.
Yeah.
Thanks.
Other questions for Mong-Han?
Yes, I do. So I don't study geodesy, so probably I'll just ask them like basic questions. So for your calculation in the southwest Taiwan, and do you consider the subsidence effect? Like, how does that contribute to your calculation?
Well, so the subsidence are really close to coastal area, so we just kind of don't consider them because there's just no way they are part of tectonics, right? And then, yeah, I guess that's pretty much how I would answer it.
Okay. And for your block model, do you consider the dipping defaults?
Yes, I do.
Oh.
Yeah.
Any last questions for Mong-Han?
I have a quick question.
Yes.
Hey, that was a great talk.
Thank you.
Really, really interesting stuff, especially with the geomorphology. I wondered if you incorporated any kind of geologic slip rate constraints on these faults
Oh, very good
for your
question.
block modeling.
I didn't, but we will. So there are some studies based on the geologic slip rate, like dating the terraces and that kind of stuff. So you can just infer the, we project it to like a long slip. I mean, a long fault slip.
Sure.
Yeah.
Cool. Thank you.
Yeah.
Anyone else?
Oh, I think there's just a question coming in.
Do you want to ask it, or would you like me to read it?
Yes, I can ask a question. Yeah, I just for curiosity, I'm wondering in Taiwan, does the major earthquake threat is by the fault line or those subduction zone interface earthquakes?
Okay. So I think,
because I think at the very beginning you showed the complex.
right. Maybe I should just share screen again.
Yeah.
Just to the talk. Yeah, we're here.
Yeah.
Right. So the subduction zone is much deeper. So above a certain depth, those are essentially collision. So you still can get some subduction zone type earthquake, but those are offshore. So those are northeast Taiwan, like eastward. Those are offshore. And actually you can get something like a magnitude 8. I think there's some kind of measurement of observation of magnitude 8 along the Ryukyu Trench. But for all the, the continental earthquakes, those are all relatively shallow, especially those really big earthquakes. Those are fairly shallow, and they are all on the west side of Taiwan. So that is a problem because the majority of the population is on the west side of the island.
Okay. Thank you.
I do have a question for your InSAR during the for the Chichi earthquake, the interferometry plot. So if my interpretation is correct, the most control was center was kind of like I think the maximum was kind of in the middle part of the fault rather than in the northern part of Trumpo. However, for the GPS observation, we see the most large slip was located in the northern portion of the fault. What's the differences?
Yeah, so if you take GPS measurements on the footwall, actually, they all kind of pointing toward this this bullseye. In fact, so this is a very interesting pattern. I don't have a GPS map to show you right now, but this is because the line of sight is a combination of horizontal and vertical motion.
Oh,
so by reprojecting that to a descending track, then you will see this bullseye. Yeah.
Okay, thank you.
Yeah.
Last